We are just recognizing that this is one way to look at the time series as having comprised of these three components. The way we identify which of these components is strong and which is not is through a method called a mathematical method called autocorrelation. What this is trying to do is it tries to find, we already know what we have heard the word correlation, right? What does correlation mean? Correlation between two variables. It measures the strength of linear relationship between those two variables, right? That is correlation, right? When correlation is positive, it's telling you that when one variable is increasing, the other variable will also increase. When correlation is negative, when one variable is increasing, the other variable will decrease. Autocorrelation, on the other hand, shouldn't say other hand, autocorrelation takes the exactly same idea and applies it to the same variable with a shifted version of itself. So this is what I'm going to do. What was I trying to see? The motivation behind this methodology was we are trying to forecast t+1 time based on as a function of y of t. Okay, just to keep matters simple, I said as a function of y of t minus 1, t minus 2, so on. But let's just try to keep the matter simple, and let's say that we are trying to explain next month's stock price based only on the current month's stock price. Suppose that's what we are trying to do. Okay, so I am trying to do, and what I'm interested in doing is finding the relationship between this month's stock price and next month's stock price. That's what I'm trying to do, right? Autocorrelation is a technique that allows you to quantify the strength of this relationship. The way I compute it is as follows. It's very simple. All I'm going to do is I'm going to list the stock prices. Suppose these are the order of stock prices, right? So on, right? This was the stock price let me write it this way. First month, second month, third month, fourth month, fifth month. Okay, I'm listing the stock prices here. What I'm going to do here is I'm going to list y t minus 1, the stock prices of previous month. Okay, now the stock price of the previous month, when I'm at the second month, what is the stock price of the previous month? 30. That's the stock price of the previous month. Stock price of the previous month when I'm here, 28, 29, 31. Right? All I'm doing is I wanted to predict these guys based on these guys. That's what I was trying to do. Right? But as far as the mathematical technique is concerned, it doesn't matter that these prices came from this. You can now at this point look at this as y and this one as x. And now you can very well talk about correlation between these two variables. Right? This is called autocorrelation of lag 1. Okay? Auto refers to the fact that it's a price series that is developed from the same series. This is called autocorrelation. When you try to find the correlation between these two prices, what you are doing is autocorrelation of lag 1. You can also talk about autocorrelation of lag 2, yt minus 2, where what you are doing is you're moving this price even down. 2 months price 2 months earlier. And you can talk about the correlation between this y and this one. This number would be called as autocorrelation of lag 2. Okay? It's not a complicated idea. You are just trying to see, is there a relationship between 1 month's price and the next month's price. That's what it's trying to quantify. Okay. If this relationship is very strong, then you should be able to do this particular type of forecast. Right? Does that sound like a reasonable thing, hypothesis? Right? We still don't know how many of these terms do we need to make these forecasts, make a good value of forecast. But we are getting there. We are trying to develop a set of techniques which will tell us how many of these terms do you need to make these forecasts. That's what we are trying. That's where we are headed. So this is called as autocorrelation. So nth lag of autocorrelation, the R allows you to compute autocorrelation through a function called ACF. So autocorrelation function. So the nth lag of autocorrelation function is the correlation between the value at a day and n days before that. That's what is the nth lag autocorrelation. So what I'm showing you here is the nth lag the autocorrelation for different lags for a stock price, General Electric stock price. Okay, the data is given here in this particular file, but let me try to tell you what the output is telling you. What the price that is given to you is the daily stock prices of General Electric for, I think, about 500 days or something like that. So the price is listed here. What I did is I produced another lagged series, okay, which had the previous day's stock price. The way I produce a lag series is in R you produce it through the lag command. Lag command, what it does is it takes a series and shifts it down by 1. Right? That's what the lag series does. In Excel, I just cut and pasted here to one cell below. Then I tried to compute the correlation between these two. That number is represented in the blue bar over here. It's saying at autocorrelation, the way Excel computes is a before I get into Excel thing. So what is being plotted here is the autocorrelation values, the blue values. What you see is that there is a high value of correlation between today's price and price 2 days back. Okay. Why might that be? If the value of price 2 days back was 30, it's highly unlikely that today's price is going to be 500. That's not going to happen. It's going to be around the same level, right? So the today's price is going to be very much 2 days back, whatever was the price was, is going to determine that today's price level to a very strong extent, right? That's what it's telling you by saying that the level of correlation at lag 1 or lag 2 or lag 3 is very high. Look at the level of correlation we are talking about 0.99 over here, right? Even when you go to 5 days later, the value of correlation has dropped slightly, but it's still well above 90%, right? So this is telling you today's stock price is a big determinant of stock price 5 days from now. In addition, I have this red bar here. Let me now talk about what the red bar is. The red bar talks about a partial autocorrelation function. What it does is something related but slightly different. Now, when we are talking about stock price, today's stock price is strongly determined by yesterday's stock price, right? Obviously, it means yesterday's and today's prices were close by. That's why today's price is going to be strongly determined, which automatically means this day's stock price is going to be strongly determined by the previous day's stock price, and that is going to be strongly determined the previous day's stock price, right? Because what I'm talking about is any day stock price is related to the previous day stock price. What that means is that I have moved 5 steps now. So the stock price 5 days into the future is also going to be correlated by this because of this one day correlation. Correct? That's what the graph was saying. Just because this is strong, the next ones will also, you expect them to be strong. They're all one day apart. So the value of correlation is not going to drop suddenly. What partial autocorrelation function captures is, when I say that 2-day autocorrelation is strong, is it strong because the 1-day correlation was strong, or is there a new strength that's introduced by this 2-day lag? That's what it's trying to find out. So it's saying, does the 2-day value provide any more information, any more extra information than what the 1-day autocorrelation gave? That is what the value of partial autocorrelation is trying to compute. In this instance, what it's telling you is, all the information that you needed to know was there in the first lag. Partial autocorrelation at lag 1 was very high. But at lag 2, there was no extra information that lag 2 was adding that you couldn't have gotten from lag 1 by itself. There was no extra information lag 3 is adding that you couldn't have gotten by lag 1. That's what it's saying. So it extracts out at each lag what is the additional information, if any, that's added by the second lag or third lag. Let me try to clear this up using a schematic. Okay. Let's say I have a chart, a line, y equal to x, right? Now this is so the data. This is the data set that I have, the time series that I have. Okay. Now, to determine the next value of time series, the only information that I need is how much did it move from one lag. That's the only information I need. And I can determine what is the next value. Right? So the lag 1 information had everything that I needed to make the prediction. I didn't need actually how much was 2 lags. Because once I got 1 lag and it's a straight line, that's the only information that I need. So the partial autocorrelation function for this would give a very strong value at 1 and no values at B. It says that the 2 lag had no new information to offer you other than what just the 1 lag gave. Okay. We will do some we will look at the different partial autocorrelation charts and then it will become clearer. But yeah. Right. Definitely, whether a value is negative or positive, it is going to tell you something. And we will talk about what it is and at what level should we take it seriously. You know, we know now that just because the algorithm gives you some number, we should not take it seriously. We should see whether it's significant enough or not. And we will talk about all of that in the subsequent graphs. Okay. So what we are going to do is this. We are going to look at the autocorrelation function and partial autocorrelation functions output for different types of series and see if you can identify for a series with trend, how does that graph look? How do this value of correlation and how does the value of autocorrelation function and partial autocorrelation function look? For a seasonal graph, a periodic chart, how does the ACF and PACF look? And for a random graph, how does the ACF and PACF look? We are going to look at these 3 cases. Once we identify that, once we understand that for trendy line, this is the way it's going to look. For seasonal line, this is the way it's going to look. For noisy line, it's going to look. Then for any random time series, you can look at it and decide does it have a strong trend component or strong seasonal component or whatever it is. Right? We'll be able to identify based on looking at the partial autocorrelation and autocorrelation charts. So that's going to be our attempt. Before we do that, I'm going to introduce one more real life data set that we are going to be dealing with. Although the pattern in this looks exactly like the birth time series, this one is different. This one is the revenue passenger miles of US airlines. So the way airlines actually measure, this is an important number through which airlines measure their performance. So they talk about how many, not just revenue, not just the number of passengers who have traveled in the plane in that particular year. They talk about revenue passenger miles. So a person might have traveled from, taken a short flight from Hyderabad to Warangal. So that's a very short distance. That distance, that flight should count less than a flight taken from here to Calcutta, right? So just counting passenger count alone does not give you full information. You compute revenue and miles together, right? Revenue passenger miles is the metric that mixes both of them and gives you. This is being actually plotted for past, I think 15 years, started around 1996. Okay, so this also shows seasonality, right? Any reason why why you would expect this to show seasonality? Vacations, right? So even though the other chart was different, and the reason why both of them show seasonality is still vacation, right? This particular dip here, any guesses what happened? 9/11, right? That resulted in a shutdown of flights for a period of a week, and then flying really decreased during that particular time. Okay, that happens in September of 2001, that particular trust. Okay, so that's another data set we'll be looking to see, how our forecasting methods work. But let's go ahead and now look at the ACF and PACF charts for some very simple series. I'm going to start with an idealized trend series, just nothing but perfect straight line. How does the ACF and PACF chart look for this perfect straight line? This is the way it looks. The ACF chart, autocorrelation function, you see is got a very high value for lag 1. For lag 2 also it's got a high value, but it's slightly lower. Lag 3 high value, but slightly lower, and so on. It's got a slowly decreasing function. The ACF is slowly decreasing chart as lag increases. Okay, but it's very high values. PACF or partial autocorrelation function, what it tells you is only the first lag had useful information. None of the subsequent lags had any useful information at all. That's what the PACF chart tells you. Okay, what you also see, this is R output, and in R nicely gives you these blue bands, which is the 95% confidence interval. Any value which is below that can be effectively considered to be 0. Okay, so values above that are the only ones that are going to be significant. That's going to be significantly different than 0. So what you see here is for idealized trend, slowly decreasing values of autocorrelation function. Large values and slowly decreasing ones. Partial autocorrelation function, only lag 1 is important. None of the subsequent lags have any extra information than what was given by lag 1. Let's look at another idealized example. This is the idealized seasonality, right? A perfectly periodic time series. Let's look at how the ACF and PACF charts look like for this. What is that telling you? Obviously, the autocorrelation function is different, right, than the previous one. What you see here is sharply dropping values, going into negative, positive, negative, positive. Why is this happening? It's indicating seasonality. What does this indicate, for example? This was lag 1. This is lag 0, 1, 2, 3 has a negative peak. What is that telling you? Sorry? Negative correlation it has, and it's beyond this blue line, so it's significant. Why would you have negative correlation? Right. So let's see this. What we see here is that, so 1, 2, here, let's talk about this one to that, right? This point, when you apply a lag 3, that is 1, 2, 3, this point, right? So this point being positive suggests a large positive number, suggests a large negative number 3 lags below. Okay, that's what it's saying all through. At lag 3, when you have current month is large positive number, indicates 3 lags before is a large negative number. That's what it's saying. What about this number? What is that telling you? At this lag, you have really positive, large positive number. Let's see what that number is. This is 0, 1, 2, 3, 4, 5, 6. At 6, you have a large positive number. Why? When you consider 6 data points away, what that tells you, you obviously get another data point at the same level. It's periodic, right? So when the value at 14 is positively correlated at value at 8. So that's why it's got a positive lag here. Is the chart clear? I can look at the time series, plot its autocorrelation function, and immediately guess its periodicity. What is the period of the time series? I can figure out looking at the autocorrelation chart, right? So you might be given a chart of heartbeat. You don't know what the level of seasonality is, right? You don't even know its heartbeat. I'm giving you some particular graph. Pass it through autocorrelation function and you can find out what its periodicity is. What is the level of seasonality on that particular graph? For a purely seasonal graph, you would have this value repeated over and over again. Positive and negative being repeated over and over again. What about the partial autocorrelation function? Partial autocorrelation function is interesting. It does not have values. Over here for large lags, you still have values. But in partial autocorrelation function, you do not have values beyond large lags. What it's telling you is the only piece of information that you need are in lag 1, 2, 3, and 4. I have all the information I need coded in just these 4 lags. I don't need any of the subsequent lags. That's what it's telling you. Does that sound reasonable? It sounds reasonable because once I figure out what is 1/2 period, I can construct the entire time series. I don't need to even wait until one full period. right? So partial autocorrelation function is giving useful information, but it's giving information that's a different type than what the autocorrelation function by itself gives. Okay, and it is saying for at first lag, second lag, third lag, and fourth lag, 4 lags are useful information. Beyond that, I don't need any more information. All the information is contained within just these 4 lags. Okay, one might take this to mean that perhaps then you need only 4 terms in this particular equation to make forecasts of future. One might make that assumption right now. Let's see if that assumption is true or not. Okay, but you do see why that comes from here, right? It's saying this partial autocorrelation function says all the information that's needed is contained within these 4 lags. So potentially those are the only ones you might need to make any future forecast. Beyond that, you don't need any forecast, any future information. Any questions? Yeah. Sorry? It is not day, it is not quarter, it is not this thing. It's for the time interval that is given in the time series. So you don't know, you don't care what is the time interval between these numbers. As far as you are concerned, this is a set of numbers that are given. The interval between each one of these numbers is constant, is fixed. That much is known. So all of these lags are in terms of how many terms you are skipping to go to the next one. That's all. That's all is needed for generating these particular graphs. Yeah. I don't think the coffee would have worn out already. Everyone is looking dull. And, sorry. Okay. So the next set that we are going to be talking about is a random time series. Time series that was generated through the random function in R. So there is no pattern at all. How does the autocorrelation function and partial autocorrelation function look for this particular case? What you see is that this number is for lag 0. Lag 0 correlation is always going to be 1. Right? It's a time series correlation of a series with itself is always going to be 1. But beyond 1 lag, there is no value, no autocorrelation at all. So there is, what it's telling you is there is no connection between one number and another number. Just because you know one number, there's no way to predict what the next number is going to be using the past numbers information. So this is the way it's going to look when you have pure noise. Okay. So we have looked at 3 separate graphs. Pure trend, how it looks. When it's pure trend, the autocorrelation function gives you high value of correlations, but it's slowly decaying. Partial autocorrelation function has information at only 1 lag, but no subsequent lag. Pure seasonality, you see this periodic pattern in the autocorrelation function. Partial autocorrelation function, you see values only for about quarter of a period, right? In the case of idealized randomness, you do not have any values that are significant at all. So you can look at the graph and tell you whether you're dealing with a random time series or you're dealing with a time series with some amount of linear determinants. So here is a summary. Ideal trend, ideal seasonality, cyclicality in ACF, and a few lags of PACF with some positive and some negative. And in ideal random, there's no values that are significant. Okay. What this is the births in the New York birth count chart. we have split that chart into trend component, seasonal component, and random component. The way it is done is using information that is there in the autocorrelation function. The function that does this is called as decompose. So you give a time series and you call the function decompose. It will split that into the trend component, seasonal component, and the noise component. That's what you're saying. And you can see that, you had all of these patterns inside in the original time series. The underlying trend part was that during the World War, the births decreased, and then they have the increase in birth and plateauing finally, right? This plateau actually goes right up to the 60s and then it starts decreasing down. The seasonal component, which was the annual seasonal component, vacation times, that's represented here. This gets added to that particular point to give you this, but it won't give you the exact value. It has this number, which is a random part, which was random variations that could happen because in a given year the vacation might have been too hot or too cold, or there is plague or some Nile virus, West Nile virus. So a number of people choose not to have babies in that particular year. That kind of factors which cannot be explained by any of this forecasting algorithms. Right? That part is all considered as a random noise. Okay. That's the split that happens, and such a split is possible precisely because we are able to study the underlying patterns in the data. So if you take this data, this is again the time series, the birth time series data. If I look at the autocorrelation function and the partial autocorrelation function, it looks like this. What do you see now? So what you see here, the values are all very high and they don't actually drop to zero quickly, right? So this is indicating it's got a very strong trend. Strong trend component is there. On the partial autocorrelation function, you do see values, large values near, but you also see values picking up near 1 year. That's telling you have a seasonality of around 1 year on the data, right? What might be the values that you might need to make forecasts using this kind of function? What would your guess be? You might need probably value at 1 lakh, 2 lakh, but you also might need values at around 1 year time, right? Because what was the value in previous February is going to determine the value in the current February, right? So this idea, this notion is slowly forming in our mind as to how this might inform us what might be the terms that are needed for us to make this particular forecast. Okay, we have in that process recognized we might need 2 nearby months data for forecast, but we might also need data from 1 year back to make the forecast. Okay, we'll put all of this together before the end of the day. But we are slowly building different pieces that are needed to make this forecast. Any questions? So this is telling you that you do need 1 lag behind as well. 1 lag behind is needed to explain the trend part. Okay, for the trend part you need the immediate lag that you need, but you need values in this case 6 months into the future. Why is it so important? See that Y has 2 level of explanation. I am not sure which level you are seeking. The simple level, the mathematical level is the data is telling you that if you choose the fifth month, half year value and the 1 year value, those two are actually significant to predict your seasonality. That's what the charts are telling you. If you're asking why might it be in the physical intuitive sense, then you might give a different kind of explanation. The reason might be that it's telling you that there are vacations that come every 6 months. This is the air passenger, revenue passenger thing. So Christmas vacations, people fly. They also fly during July vacation, and it's probably indicating that wasn't there in the other time series. So this is only a guess, right? But it does make sense. It makes it sounds plausible. No, this was the revenue passenger. The other one looks similar, but this one has additional structure here and here. The other one had this more stronger trend one. This one has a drop and then again increase. That's probably the July and December month. Is the idea clear? Yeah, I won't say only yet, okay, but all I want you to think about it, it looks like these might be the bare minimum information that is needed, right? Do we need more information or not? We'll come there in a bit. Absolutely. So look, as a data scientist, your task is making forecasts, right? It's the sociologists and the business majors who do the why part of it. I'm not saying we should not be interested. We absolutely should be interested in it. In this case, my guess is this. And the way for the business major, they'll actually have to check it, right? And the way you possibly would check this, any ideas of how you might check whether that is true or not? Whether, people who took when a given July vacations are not taken, the corresponding one is that higher or not? Right. So you look for some events that happen in a during around July where the sales were impacted, and then you follow through and to find out is there a correlation on those particular years. That's the way you would analyze the data. I don't know whether that actually happened here or not. No, but the thing is, I don't know if you're realizing, you guys are getting the tool sets that you have in your arsenal is increasing enough that now you have techniques through which you can make those conclusions, those analysis, right? All you need is the ability to think and not be afraid of complicated looking patterns. You can get reasonably intelligent information looking at these charts. Any other questions? So in this case, this is the decomposition of the revenue passenger mile chart. Again, that can be split using the decompose function, and it does show you the broad trends where the trends actually looks like it was already dropping before the September 11th happened. And that is actually true. September 11th, 2001 is when the planes hit. But when did the dot-com bust happen? Anyone remember? Shortly after the 2000, the Y2K problem is what led, the whole, exporting of software engineers from India, right? Because they didn't know this Y2K bug. Okay, you guys are too young. I don't know if you even know what Y2K bug is. You guys know what the Y2K bug is? So that when the people realized that software applications were not coded for 4 years, they were coded for only 2 years. So years was entered as 98, 97 instead of 1998 or 1997. What that meant is that when your year 2000 rolled around, year went from 99 to 00, and no one knew what was going to happen, because there were different algorithms which are making this inherent assumption that the year value will need to be constantly increasing. Nobody knows which particular module in which particular software will fail when the year value actually decreased or had a zero value. So they needed to increase all of them to four digits, and this was a huge industry. Infosys was created, Satyam was created, all these companies made big money during that time. And once that problem went off, suddenly you had the dot-com bust. I mean, there was also a variety of other things happening around the same time. So this drop that you see happen was already happening before 9/11 happened. 9/11 just made the recovery worse. That the time taken for recovery became longer because of 9/11. Anyway, this is showing all of those trends and seasonality. The nice thing is you'll be able to look at these graphs and make these nice conclusions. And what you do see is that the impact of 9/11 showing up on the noise factor. Why is it showing up in the noise factor instead of seasonality or in the trend? It was an unpredictable one. None of these time series methods could have predicted a 9/11 could have happened. As far as 9/11 was concerned, as far as time series methodology is concerned, that's a noise event, which was not predictable through seasonality or trend. Excellent. So that's why it's showing up on the noise part of the time series. Okay. So thinking whether we should take a quick break now or 5 minutes later. Okay. Now, quick 5-minute break, and then we'll talk about. So what we did for the past half an hour or so, or 40 minutes or so, was we didn't actually do any forecasting techniques. What we did was we looked about a way of analyzing time series and making conclusions about time series, whether it's got strong trend in it or if the time series has seasonality in it. How do you make this conclusion in an objective way without having to just look at the graph and deciding whether it's got seasonality or not, right? We already talked about why looking at the graph, it's going to be just a subjective decision, right? What we have developed now is an objective metric of deciding whether a given series has strong trends or strong seasonality, or what type of series is it. We developed this objective metric, which is ACF and DSCF. Both these charts, both these functions have different information, and it's important to look both of this to decide whether it's strong trended one or it's strong seasonal one, or if it's a mix of both of them. Now, now that we have talked about this analysis technique, let's talk about how we actually make forecasts. Okay. And the way we are going to do this is by slowly building models of increasing levels of complexity. Okay. The very first set of models we are going to be talking about are simplest models you can think of, and we'll slowly keep increasing the complexity of the model. And by the end of the class, most of you will be banging your heads on the desk. Like very complex models, but we'll talk about why we need this complexity, and even though those models might not be as intuitive as you would like, it's not going to be completely opaque. You still know what the model is trying to do, and thankfully we have R these days, which will allow you to make these forecasts using these complex models without having to do terrible amount of coding. Okay. Now, in all of these forecasting methodologies, one thing that's essential is, when we talked about regression, one of the things we talked about as being important is this idea of homoscedasticity. The fact that the variance in the data be constant throughout the data set. Right? That is a useful feature in any forecasting problem that you have. In the context of time series, we talk about that same idea as stationarity. Basically saying, when your given time series have constant statistical properties of mean, variance, and autocorrelation, whatever, over time, then you say that the data is stationary. If the values, if you look at the mean of the first year and the mean of the second year and the mean of third year, so on, if the mean is changing over time, or if the variance of first year is very different from variance of second year and third year, so on, forecasting is difficult. So what we try to do is we make the data, try to do some transformation to the data, which will make the data into a stationary data. The idea should not be new, because that's exactly what we did in linear regression as well. We called about as homoscedasticity, and we tried to do some transformation which made it any heteroscedastic residuals into homoscedastic residuals, right? Even here we are going to do another transformation, but the transformations that we are going to be talking about are simple transformations. Let me first show you an example of a series. Now, this series is where, if you look at the this is the General Electric stock prices. If you look at the stock prices over the first quarter, second quarter, third quarter, fourth quarter, so on, this is a daily stock price. Okay, you would see that the price mean value is going to be very different. Okay, depending on different windows, the mean value is going to be different, and in different windows, the variance, the standard deviation of the prices is also going to be very different. This would be what we call as a non-stationary data. Okay, so how do we stationarize the data? The way we stationarize data is through a very simple method called differencing. So here is the price data: 17, 16.63, 16.86, and so on and so on. Okay, what I'm going to do, I'm going to take this data. This is data on day 2, data on day 1. I'm going to create a new series, which is the difference between day 2 and day 1. Okay, so this series, if you look at it, oh man, that number is small. It's the difference between B3 minus B2. B3 minus B2. Over here, it is the difference between these two. Over here, it's the difference between these two. So the value, everywhere, what we have done is a different series. Essentially, what this series is doing is how much did the price move from yesterday? How much did the price move from yesterday? That number, if I look at it, the different series, if I look at it, that number, they're all scattered around 0. So the mean value does not change. Okay, this particular series actually has heteroscedasticity. Can you see that the variance here is higher and the variance here is smaller, right? So what people do is, when the series does not look stationary after one differencing, what you might do is you might difference it again to see does it become stationary now. Okay, so that is the second column. This is first differencing, and the second one is the second differencing that you are doing. Now, the idea of differencing should remind you of uh, uh, another concept, a similar concept, which is numerical differentiation. How do you take derivative of a curve on a computer? I have data points. I'm giving you a parabolic curve. Okay. How do you take the derivative of this curve? Slope between immediate points, right? That's the way you take derivative. So what do you do? This is y1, y2. You take a difference of y2 minus y1 divided by delta x, right? Delta x is same as everyone. So if you just plot y2 minus yt minus 1, that data is going to look like, for these values it's going to be negative, and then it's going to become positive for these values, right? When you take this data and do a numerical differentiation is nothing more than differencing of two intermediate steps. Then that is called, so the differencing process should remind you of numerical differentiation. Okay. Now, if a time series on differencing, when you take a difference between immediate numbers and create a new time series, if that time series is stationary after differencing it once, you say that that time series is integrated of order 1. Okay. It might seem funny that you are differencing it once and you calling it as the original time series is integrated. The reason why the word integration is used is, when you have created the time series, an existing time series, after differentiating once, it is a stationary series. So to get the original series, you are integrating back once. So you say that the original time series was obtained as if it was obtained from integrating a stationary process. So the original time series is called as integrated of order 1. When you need two differencing to create a stationary series, then you say that time series is integrated of order 2. Okay. I'm just saying this definitions verbally. We'll come back and before the end of the class, we'll write it up formally as well. But I just want you to keep that value in mind. So how about, let me see if you guys have a intuitive sense built already or not. I have a time series that looks like this. Is that a stationary series? Is that a stationary series? So think of it. Is the mean of windows, when I take a mean of different windows, is the mean going to be constant? The mean won't be constant. The mean is actually, mean of windows is increasing. What do I need to do to make it a stationary? Difference it, right? When I take this difference, it's going to be some number. That's going to be the same number here, same number here, same number here, right? So when the difference series will look like this, right? This series, I'm going to say that this series is integrated of order 1. What would be a series that is integrated of order 2? What would be a series which requires differencing twice before it becomes stationary? Parabola. When I take a parabola, when I difference it once, it will become a straight line. I need to difference it once more to make it stationary, right? So it requires two differencing to make it stationary. So that parabola type of series is a series that requires differencing of order 2, right? So you say that series, the original series, is integrated of order 2. Okay. The definition might seem inverse, but if you get the idea, and say that this is convention, Let's stick with the convention. It's called as integrated of order 2. This will be integrated of order 1. All I'm trying to do is build some intuition about when you might need to difference a series and when you might not need to difference a series. This is a series that needs to be different because the value of the mean actually changes over different windows, right? This looks pretty much, this would be a stationary series. So the way you create differencing, so the way you create stationary series, one method of creating stationary series is actually through differencing. In financial time series, the most common way to create a stationary series is not just differencing, but instead try to compute percentage change from previous year. Instead of how much did the price change, you compute the percentage change from previous day. That is the most standard way of creating stationary time series for financial, in the financial application. But most of the other application, you just do difference. So in the case of General Electric stock, if I plot the autocorrelation function, what does this autocorrelation function look like? What does it remind you of? Trend line, like a straight trend line. So the original time, if I take GE stock's original time series and look at the autocorrelation function, it looks no different than a straight line trend. Trend is overwhelming it. That's because the data is actually non-stationary. I can stationarize the data by taking a differencing of the G. When I do that and compute the ACF and PACF, what does that now remind you of? No trend at all. The 0, there is autocorrelation 1, but none of the lags have any other significant autocorrelation. PACF also, almost none of them have anything significant. This is how random noise looks like. Random noise look like this. There are some values which are slightly above your 95% threshold, but it's barely. We are talking about correlations of 0.7 or 0.8%. Or sorry, 7 or 8%, not 0.7, 7 or 8% correlation. So the very small this thing. So the difference GE series looks pretty much like random noise. So there's actually, this is the reason why it's very hard to predict stock prices. People talk about stock prices are equivalent to random walk, or the movements cannot be predicted using any of the standard time series methodology. There is a reason they say that. It's because the amount of information in the lagged data is not that much. This is why making future forecasts of stock prices is extremely difficult business. So a non-stationary series has an ACF that remains significant for half a dozen or more lags. So you must difference the series until it's stationary before you can identify the process, whether an underlying series has trend in it or underlying series has any seasonality in it or not. Before you make any of those conclusions, you need to difference the series and make it stationary. Okay. Now, suppose you do have a time series that is actually stationary. So here I have a series, set of values, they're all varying around the same level. This is some stationary data I have. And I want to make forecasts of what the next value is going to be. Let's talk about what are the possible methods that are there. Now, I would remind you of the very first forecasting problem we did, even though we didn't call it forecasting at that point, which was the Kingfisher number of overbooking seats. That problem we did. What is the forecasting we did there? Mean. Right? Mean is the easiest and most, the simplest forecasting one can do of the problem. In this case also, that's what we are going to do. We are going to say the best forecast of this data, or the easiest forecast of this data, not the best, is going to be the mean value of some previous n number of values. For example, you might choose previous 4 values. So at any point of time,